Welcome to Transfer Phenomena in Bioprocess Engineering NPTEL course, week 1. So, we will discuss today class fundamental of transfer phenomena. Why mass transfer is very important? Already we discussed the different type of mass transfer, then heat transfer, momentum transfer. There is a three type of transfer is there: mass, momentum, then heat transfers. So, why mass transfer is very important? Because here very essential for nutrient uptake, then oxygen supply, then you want to remove the product also. For this all with respect to mass transfer only here is works here. Then there is a rate limiting in aerobic fermentation. Example, oxygen transfer. Then other one is for mass transfer affects yield, then productivity and then scale up. So, what is the mechanism of mass transfer here? The mass transfer mechanism here: diffusion, then convection, then interfacial transport. So, what is the diffusion here? The diffusion, molecular movement due to concentration gradients. I already discussed the same thing. The dou C by dou Z is a gradient. If you only talk about dou C or delta C, that is a concentration difference. We should know what is the difference between concentration difference and then concentration gradient. Then convection, how convection here? The bulk movement of the fluid carrying the solids. So, what is the interfacial transfer? Interfacial transfer between the phase gas liquid or liquid solid. So, what is molecular diffusion? So, there is a two type of mass transfer. One is the molecular diffusion, then eddy diffusion. The mass is here transferred by the random molecular motion across the concentration gradient. Normally, this will be always called natural, but eddy diffusion, it is like convection diffusion, because here mass is transferred by the finite parcel of, in case of like momentum and heat transfers. So, there is what is the molecular diffusion definition here? The net movement from high to low concentration. There is a concentration moving from high to low concentration, that we call as a molecular diffusion. So, the best example for tea from, there is a tea bag is there in hot water, you just drop it, the tea bag in hot water, then how the diffusion taking place. It is like simple that once if you drop it here and you allow as it is, that is called a molecular diffusion. But once you start to stirring here, you take small stick and just stir it, then the diffusion starts, that always called as a eddy diffusion, because since you are disturbing, then because that is, or we can say convection diffusion. So, then the diffusion starts. So, the rate of molecular diffusion, what is the rate of molecular diffusion here? The function of molecular velocity and the concentration gradient, that is a rate of molecular diffusion. So, what is the driving force of mass transfer? We discussed so many times, the concentration gradient is a driving force for mass transfer. So, this is a famous Fick's first law. So, we always write J proportional to minus of dC by dx. Okay. This is a Fick's first law of diffusion. What is J? The J is a mass flux. Sometimes we will write molar flux. We have so many different flux are there. So, this units here kg per meter square then second, or we can write kg mole meter square second. Any rate of this one divided by per unit area per unit time meter square per second. So, that is called mass flux or molar flux. The C stands here concentration, that the units is kg per meter cube. Then the distance here, what is the distance of this one? That normally the mass transfer traveling from one place to other place, the distance we called as the x. So, d is the diffusivity. You want to remove the proportionally constant, then remove this one, j equal to minus of d dou c by dou x. So, the d called as the diffusivity, that unit is here meter square per second, but the d same thing we call as a mass transfer diffusivity. We already discussed what is the different type of diffusivity here. The d stands here mass transfer diffusivity, the unit is here meter square per second. It is a famous first law, Fick's first law of diffusion. So, if you want to study the mass transfer, of course, we need thorough knowledge about the this one Fick's first law of diffusion, what is the Fick's second law of diffusion, all. So, whatever discuss same thing, there is a Fick's first law of diffusion, whatever J equal to minus of D, this one, the flux and this all diffusivity, but this always is steady state diffusion. Why here, if you not introduce for dou C by dou T until, then we call always that called as a steady state. If you use this dou C by dou T, then calculate, then it's called unsteady state, that is a different here. So, the Fick's second law here, the dou C by dou T equal to D of dou square C by dou x square is the second order. Of course, some other term also will come, but we neglected all to make life easy. Then we are writing like dou C by dou T equal to D of dou square C by dou square. It's a Fick's second law. It's always discuss about the unsteady state, because there is a time here, the time derivative is there, that's called unsteady state. If there is no time, if we make this is 0, accumulation 0, then we can call as this a steady state. If it is time dependent, but here it is a time independent, if time dependent, then we will write for this one same way unsteady state. So, it is very important for the transition then for nutrient supply, especially in the biofilm. So, just basic some this one, what is the film theory of mass transfer here? The mass transfer occurs through the thin stagnant film at the interface. So, what is the driving force here? The driving force here, concentration difference across the film. What the rate depend on the diffusivity and then the thickness of the film. So, what is gas liquid mass transfer? Gas liquid mass transfer here, it is a very important for in the aerobic fermentation. Then there is a OTR, oxygen transfer rate, OTR equal to KLA, there is a KLA, then the C star minus C, that is the oxygen transfer rate, we call it as the oxygen transfer rate, OTR. So, oxygen has the low solubility in water especially, so it is often limiting steps here. Then here the KLA is the mass transfer coefficient, overall mass transfer coefficient. Then the T stands here saturation concentration, then the C is a actual concentration. So, that is a difference between saturation concentration then actual concentration, the KLA. The KLA here, the unit of KLA, the KL is meter per second, it is come like, then the area, the interfacial area, that is a meter square by meter cube, then here kg mole per meter cube. Okay. So, then you just see here, so KLA, so this is wrong. Okay. So, we will get here OTR, OTR is the oxygen transfer rate here, then this K is the different units are there, this we called as a interfacial area, then the C star is the kg mole per meter cube. So, finally, we will get in terms of kg mole, these units we can say here second inverse. So, I will repeat here, this is meter per second, then here the meter square per meter cube. So, if we cancel it these two, then these units KLA units here second inverse or whatever minute inverse like that will come. So, there is a unit, there is a lot of, okay, here already is there. See here what we discussed same thing, the KLA, the work example for how the oxygen transfer here, the KLA 200 hour inverse. So, convert a second, then C star, there is a C star the concentration of saturation, okay, the saturation concentration, then other is for actual concentration. So, all consider that and we can get from here OTR value, this is the OTR value. So, what is here the OTR increases with respect to when it get agitation and aeration. Okay. So, what are the factors affecting KLA, the overall the mass transfer coefficient. So, that is agitation speed. If agitation speed is you want this one, then definitely it is improve the bubble breakup and then dispersion. So, if it then aeration rate increase the interfacial area, then viscosity of broth, the higher viscosity always reduce the KLA value. Then next is the lossless impeller design that determines the flow patterns, it determines the flow pattern. Then mass transfer in downstream process, where we use here the dialysis part, first part, there is a solute diffusion across the membrane, then ultrafiltration, there is a selective separation here, then the chromatography, it's diffusion and convection combined here. So, what is the case study of oxygen limitation in large fermenter? You take industrial fermenter always the volume of the fermenter is very high. So, its face definitely oxygen limitation. The cells in the center received less oxygen because the volume is very high, to definitely they reduce the productivity of that one. How the solution of this one? Then you have to increase the agitation rate is higher agitation rate, then oxygen enriched air we have to use, then better impeller design. So far we discussed regarding this mass transfer, this one. So what is the conservation of mass? Is a very basic things when you want to go bioprocess engineering in the transfer phenomena. So we need some basic here. Here conservation of mass, we write like normally the simple mass balance, you just see here input equal to output then plus accumulation. So normally the conservation was how you have to start, you assume as a steady state. If you assume steady state, then automatically the accumulation gets 0. So what is input and output here? Say example here, the input we can write always input IP, output then plus accumulation. Okay. This is the normally the mass balance. If you want to write a mass balance, input equal to output plus accumulation. So here the steady state, whenever if you talk about steady state, the accumulation gets 0, then we can write rate of input equal to rate of output. The very basic consideration of mass equation. So here in terms of if you write here, so with the simple for continuity equation, how it works here, V1 is the velocity at point 1, you take point 1 and this is a point 2, and the rho 1 is the density of this one, the A1 is the area, same way for A2. So at point 2, velocity 2, the density 2 here. So this is a famous here, m dot equal to the continuity equation, m dot equal to rho 1 V1 A1. The rho here, rho stands kg per meter cube, density, then this is a velocity meter per second, then A is the area meter square. After solving we will get the kg per second, that is a mass flow rate. So if we rho 1 rho 2 same, then we can write m dot by rho equal to q, that is a volumetric flow rate, because here m dot is a kg per second, then the rho is a kg per meter cube. Once solved, then we will get a meter cube per second, okay, for volumetric flow rate. So that is called V1 A1 equal to V2 A2. So a simple problem, we have two type of this here, water here, then other one is alcohol, the water volumetric fluid here, that is a 0.1 meter cube per second, then alcohol volumetric fluid is here, both you are passing through the Y shaped this one pipe. So here then what is the average density of when you mix together in alcohol water, what is the average density? So we assume the water 1, alcohol 2, then the mixture is 3, because you want to write very easy to this one. So rho 1 is density, then rho 2 alcohol, what is the density? Same way Q1 is what is the volumetric fluid of water, then volumetric fluid of alcohol. So we can write the same way Q1 rho 1 equal to Q2 rho 2, Q1 rho 1, Q1 rho 1, Q2 rho 2 equal to this say Q3 rho 3, the summation of this one. So we know the value of Q1 because already problems already given. Of course rho 1 we know, you just substitute all the value, get the value of Q3 rho 3. So the Q3 rho 3 we called as the M3, that is a mass flow rate. So then if you want the rho 3, then simple addition of Q1 plus Q2, summation of this one Q3. So already values are there, 0.1, then 0.3, the 0.4 here, you get the value of density, that is called 850 kg per meter cube. So, another example how the raw milk is flowing into the centrifuge through the 5 centimeter diameter pipe, velocity 0.22 meter second, and then it's and in the centrifuge is separated into a cream of specific gravity 1.01, then the skim milk of the specific gravity 1.04. So, very simple, then calculate the velocity of flow, the skim milk of the cream if they are discharged through the 2 centimeter diameter pipe. There is a specific gravity of raw milk is there. Okay. So, anyway, diameter d1, of course, the problem already given, that is a 5 centimeter, then velocity is there v1, velocity v1, diameter d1, same way for d2, diameter d2 already given. So, we do not know the value of v2. So, anyway, this equation we know q1 rho 1 equal to q2 rho 2 equal to q3 rho 3 is a conservation of mass equation. Then raw milk equal to summation of cream milk plus skim milk. So, rho 1 v1 a1 equal to you add rho 2 v2 plus rho 3 va3, it is a mass of continuous equation. You substitute all, then we get the value of this one. Then you want to write a volume balance except this one, we will get a one more balance v2 plus v3 equal to 1.375. So, basically solve the both equation, then we get a velocity of cream milk 0.229. So, velocity of again the skim milk is here 1.145, this one. So, it's a very simple problem here. Next, why dimensional analysis we have to use? Dimensional analysis, there is no units, then it is called as the dimensional numbers. And here the fundamental quantity we always write m, mass m we used to write, then length is L, length of this one L, then a time always we write a time T, then a temperature is a T. So, totally 4 the fundamental quantity here, we discuss how you have to write the fundamental, it is a famous Buckingham theorem is there. So, there is a q minus u. So, you want how many variable q is there, total how many quantities or how many variables are there, then the u is the fundamental units. What is the fundamental units here? So, the q minus u we get that much dimensional numbers here. So, the p is the dimensional group 1, 2, 3 like that. Repeating, q is the variable and the u is the what is the fundamental units of that one. Fundamental units like m, mass, length, time, temperature is a fundamental here. So, after insert this one, then we will get this many dimensional numbers. So, example for incompressible fluid, the flowing inside the circular tube of inside diameter d, then what are this one? So, definitely the pipe diameter is there is a pressure drop, one is the main thing, then velocity v, then the diameter is d, tube length we called L, and viscosity we use write mu, okay. Then other one is for rho, rho is the density, okay. So, rho is the density, then here the q equal total number of variable here, because total number of variable here q equal to 6, q equal to 6. So, we will write a small, not the capital letter, okay. We will write q equal to 6. So, q equal to 6, that is a variable, then the fundamental unit dimension is u equal to 3. So, we will get a 3 dimensional group here. So, this unit is already known, pressure drop we write Newton per meter square, then after that if you want the conversion of dimension m by L T square. So, that pressure drop is the force by area, then the force you can write MA, m is a kg, just one I am doing, meter per second square, then area again meter square. So, finally, we get kg meter per second square meter square. You can cancel this one. So, kg we can write mass m, then the second square T square, this m we stands here L, that is only first one. So, diameter the L here, velocity meter per second L by T, then the L is here, L is again unit m, the viscosity kg per meter second we can write m L T, m stands mass then L stands this length, then T stands here second. So rho is the density kg per meter cube. So make sure that these all dimension numbers are there. For example, pipe diameter. So the P1 equal to function of P2 and P3. Of course, then we have to fix the what is the core variable here. The core variable here, one is the diameter, then one is velocity, then another one is the density. We have to take all three. The density of these are the core variable here. So density here, one is the diameter d, then v, then rho. Diameter, velocity, then density. So this is the main core variable here, we mentioned here. So the pi 1 is a group of that one. Okay. So we call it P1, P1, P2, P3, then the delta P1, another, see totally we have 6 variable. So 3 variable fixed, another 3 variable we have to pick. One is the pressure drop, then other one is for length, then viscosity. So make a dimensional group such a way that you take the first one. Now we made a 3 because the here dV rho are core variable. So the delta pressure all other variable. So again now you take the first one is dimensionless numbers, first one the P1 equal to so first take diameter d, this is a L, you write d power a because totally 4 variables are here, d is a L, then here velocity, velocity power b, then another is a density power c, then the pressure drop delta p, okay, because this is a variable. These are the core variable and this is another variable. So after solving now, so you can take first, you take only L, you take only L here. L if you take the first one is for A, then B, here we have to write a minus 3, 6 is the down, we have to write a minus 3C, then what is L here, L here, okay, there is a M here if you stand plus, but here negative, okay. So we can write minus of 1. So such a way that we have to write like the A plus B minus 3C 1 for equal x to exponent to the M also, write C plus 1, then for time you write 0 equal to minus B. The time here, this is a time here, okay, there is a one time here and here also, that's only minus B minus 2. When you solve this equation, it's a very easy because you can solve from here, then the B equal to directly minus 2 will come. Once you know B, then C also we can get it from here minus 1. You get the value of both C and B, then substitute here, then get the value of A. So now you know A, B, C. So what we are doing here, A, B, C, this A, this value, A value, B value, C value, we got answer. Okay. So anyway here already delta P is there. So this just substitute that one, then we can write here B stands V because square is there, then the C here minus 1, that's a density. So finally we got this equation, this this dimensional numbers, we call as a Euler number. This we called as a Euler number, the P1, first one. The second one here, second one same way, the P2 here L by D. These are dimensionless numbers again, one more. Then another one is a P3, same way we have to solve. How to solve? You take another equation, this equation, you pick up this one, then you do like this way, then we will get that one, okay. It's a very simple. Same way for here also, if you do this one, then we will get, you have to use the regular, the routine procedure, then we will get this one. So example here, the third one is here, the P3, that's a mu dV rho. Once you solve, we get the Reynolds number here. The Reynolds number, we always discuss that one, dV rho by mu. These are Reynolds numbers, okay, dimensional numbers. So then you make it this one, this is anyway is Euler number, the function of L by D is Euler number, function of L by D, then the reciprocal of Reynolds number, 1 by R is the reciprocal of, is the Reynolds number here. So finally F is the, we know already friction factor, from there we can get a friction factor also, F equal to delta BD by 2 of, maybe we can discuss sometime, this we always solve the friction factor. So far we discussed the incompressible fluid, how the pipe flow this one, what are the dimensional number here. But what are the common mistake we will do here? Sometimes we choose the wrong variable, or sometimes we will extra variable, or some missing the important variable. Make sure that this one. Sometimes it leads to incorrect the pi group, whatever the p group, dimensionless group here. So, but then experimental analysis based on the results may mix the significant changes, because that is not there. Okay. So, very important to initial choice of variable is a very important. We have to be very careful to take this one. So, the dimensional heat transfer, so far we discussed in the MOS. Then what is the heat transfer here? Same way the Buckingham method we will use, we are going to use same method, but here the variables are, okay, heat transfer pipe here. What is the heat transfer? Assume the heat transfer pipe. So, here the fundamental, the dimensions here, this is a q minus u, same way the q is the total number of variable, then u is the fundamental units or dimension, like m, mass, length, time. 6 the heat transfer involves temperature. There is no heat transfer, that is only we did not introduced here, the temperature we have to introduce. So, totally 4 we have fundamental here, the total variable how many here? We saw 7. So, 7 minus 4, same way we will get the 3 dimensionless numbers from this one. Okay. So, here again what are the variable for this problem? We assumed as this heat transfer in the turbulent flow, how the dimension numbers behave here. So, the H is the heat transfer coefficient. So, D is the diameter, the rho is the density, mu is the viscosity, the specific heat, K thermal conductivity, V is the velocity. So, the total number of variable Q equal to 7, the fundamental here U equal to 4, that is a M, length, time, temperature. So, after solving this one, then we will get total 7 variable, then fundamental 4, we have to get 3 dimensionless numbers. So, H is the watt per meter square Kelvin, but in terms of dimension we can write MT3T. The T stands here second, but this T is the temperature. One is the temperature, other one is the time. This T is the time. That is very important. So, then again velocity, D diameter, viscosity kg per meter square, the density, then the specific heat we can write joule per kg Kelvin, the K is the thermal conductivity watt per meter Kelvin, then there is a corresponding dimension. So, we can write the meter always, that is the length. So, then density kg per meter cube, kg mass, then meter cube here L3. We already done the same way Q minus U, the Q is the total number of variables, 7 variable. I will go back, 7 variable, 1, 2, 3, 4, 5, 6, 7, totally 7 variable. The fundamental here 4, mass, length, temperature, time. So, once you make it this one, then whatever rest everything, 7 minus 4, 3 dimension numbers we are get. First we have to choose the core variable, because we have so many variables are here, which is a core variable which is essential to do this one. So, that we have to check. The here core variable we choose the D, diameter, K, then mu, then V, because it should not repeat. Sometimes if you choose the viscosity, there is no need to choose again density as a core variable, because already viscosity is here. Same way you can avoid always. If it heat transfer coefficient is there, already thermal conductivity is there. So, we can choose only 4 core variable here. Okay. So, after this 4 core variable, then other are heat transfer coefficient, then Cp rho. So, you take the first one, we can solve it, the pi 1 equal to dA, you take the first one dimensionless group here, pi 1 equal to dA kb mu c vd h. You have to solve this one. Okay. This is the same way, the dimension numbers we write, because we have 4, but the previous problem only 3, m, l, t, but here extra time, temperature, there is a temperature T is here. So, once you introduce this one, so the first one is for diameter, diameter L, then thermal conductivity K, we can write K power B this way, then viscosity mu C, viscosity, then that is a velocity V power D, then the last is a H is the heat transfer coefficient. Now you take the variable L, M, T, D, then solve it. Then the first one you can first go like this. I will just, because maybe you cannot understand. So here there is a T temperature, that's a B equal to, first get the value of B equal to some value -1. So once done B, then here you substitute, then get the value of C. So once you know C, then B, you substitute here, get the value of D. So you know D, then or you know D, you know the BAV, then finally you can go to here and get the value of A. So after solving everything, we know A, what is B, what is C, what is D. So you substitute here, then the dimensional numbers here is called HT by K. We called as a Nusselt number. Is called a Nusselt number. We will discuss more on forthcoming classes. What is the significant Nusselt number? What is the unit of Nusselt number? Everything we will discuss the forthcoming classes. Then the pi 2, another dimensional group here, pi 2, that we write as Cp mu by K. After solving, how you are getting? You take this equation, the first, okay, you take this second one, then solve it. If you solve it, then we will get a pi 2. Then same thing, this one you take it, then solve it, then we will get a pi 3. This is a third dimensional numbers. So 3 dimensional numbers here, pi 3 is a Reynolds number, we called a Reynolds number. So finally the HT by K, that's a Nusselt number equal to function of Reynolds number, then the Prandtl numbers. So this we will use for, this is a very familiar equation for heat transfer inside pipe. So you know Reynolds number, you can always, it's like analogy, you can take from here, we can find the other mass transfer, some other, okay, heat transfer. So it's very easy to find other values. So what are the key takeaway here? Whatever is very simple, we discuss about what is the diffusion occurs in the concentration gradient, then the Fick's first law, the steady state diffusion, then Fick's second law, steady state diffusion, what is the oxygen transfer control in aerobic fermentation, then the continuity equation also we discussed in the conservation mass, then Buckingham theorem, it's reduce the experimental complexity, because from there we derive the dimensionless here. Then we got some idea about the what is Reynolds number, what is a Nusselt number, what is the Prandtl numbers for the transfer phenomena. Thank you.